Samuel, we had learned about linear motion, right? Or linear motion is also called translatory motion.
Yes.
In all the previous chapters, right?
Yes, sir.
We have been talking about linear motion, or rather, motion in a straight line. Based on that, we have discussed equations, we have discussed concepts, correct?
Yes, sir.
Okay. So another name for linear motion is translatory motion, all right? Now can you tell me some variables which are important in translatory motion? What did you learn? I'm sure you have been learning about translatory motion right from a lower class, correct? Translatory means linear motion, all right?
Right.
So what are the terms you have been learning?
Distance, displacement,
Very good,
speed,
very good, very
velocity,
good, very
etc.
good. So you have been learning about displacement, you have been learning about velocity, you have been learning about acceleration, correct?
Time.
Of course, yes. Momentum,
Yes, sir.
force, correct?
Yes, sir.
What is, how do you define velocity?
dx by dt.
Good. Or I can say ds by dt, if s is displacement. How do I define acceleration?
dv by dt.
Very good.
Change in velocity with respect to time.
Sorry?
Change in velocity with respect to time.
Rate of change of velocity. What is momentum?
Mass and velocity.
Right. How do you write force? What is force?
ma, mass acceleration.
Yeah, mass into acceleration is one way of writing it. Another way of writing it is from the definition. Rate of change of momentum with respect to time. That is how Newton's second law defines it, correct?
Right.
Then when you substitute for P mv, then you will end up getting mass into acceleration, right? What is the expression for kinetic energy?
Half mv squared.
One more I ask you to remember, right? Yes, Samuel?
p squared by 2.
Did I tell you this?
Yeah.
Yes. Okay. Now we come to rotational motion, right?
Yes, sir.
Okay, when I talk about rotational motion, right? We talk about a body which is called as a rigid body. What is a rigid body? If you apply a particular quantum of force,
Right.
the body doesn't get deformed. That body is called rigid body. For example, let's say you take a sponge, you apply some force. Do you think
Yes.
the body is getting deformed?
No.
No, it will come back. But point is, as you're applying the
Gets
force,
deformed, yes.
yes, right? So then it is not a rigid body. Suppose, let's say you take a metal box. You try applying some pressure. Does it deform?
No.
Right. So you can, for your practical application, you can say that is a rigid body. All right.
Yes, sir.
Suppose you can obviously crush anything with enough force.
Right.
Correct. So you can always prove that there is no body which is rigid really.
Right.
The point is, for our practical application of forces, we can say that in comparison with, let's say, a sponge versus a box, made of metal. A box made of metal is going to be more rigid.
Rigid.
Right, Samuel?
Yes, sir.
Yes. Okay. So for a rigid body, let me talk about this. Let's say this represents a rigid body, and this rigid body is going to rotate. So always what is important is rotation about an axis. So keeping this as an axis, the body is going to rotate. For example, Earth rotates about itself, correct?
Yes, sir.
So there is an axis, isn't it?
Yes, sir.
Right. So this axis is called the axis of rotation. So are you able to visualize?
Yes, sir.
Okay. Now, just how you have these parameters like displacement, velocity, acceleration, momentum, force, kinetic energy, all this in translatory motion. Similar quantities are there in rotational motion, which are very important. See, in rotational motion, we are not very much concerned about linear displacement. Why? Let me explain to you. Suppose, consider this pen, right?
Yes, sir.
Okay, consider this pen now. Now, let's say this point is A and this point is B. Okay.
Okay, sir.
Now, let's say this body is undergoing a straight line motion, which is translatory motion, right?
Right.
Suppose, let's say I move it for 2 seconds, and let's say it has covered some 30 centimeters.
Okay.
What is the displacement of the point A? I have to move this object by 30 centimeters. I'm asking you what is the displacement of this point A? Thirty centimeters, right?
Oh,
See here, I move an object by 30 centimeters. What is the displacement?
30.
That's what I'm asking. So what is the displacement of this
30 centimeters.
point? What about this point?
Also 30 centimeters.
That's what I'm trying to say, right? So in linear motion, if you see all the points on the, let's say this is a rigid body, for example, all the points on the rigid body travel equal displacement, correct?
Right.
Right. Similarly, now, what is the velocity going to be, Samuel? Average velocity. Let's say it has covered 30 centimeter in 2 seconds.
Okay.
So what is the average velocity
30
of
by
point
2.
A?
30 by 2.
30 centimeter by 2 seconds, right? So 15 centimeter per second, correct?
Yes, sir.
What is the velocity of this point B?
Also 15 centimeter per second.
Very good. So in a rigid body, all points have same velocity in translatory motion. Is that clear?
Yes, sir.
And similarly, acceleration will also be same for all the points, correct?
Yes, sir.
Now, if you consider rotational motion, now we are going to talk about rotational motion, all right?
Yes, sir.
Let's say this is my axis, okay? About this axis, this body is going to rotate. Are you able to visualize?
Right.
Okay, now tell me one thing. Let's say this is my axis, okay? This shows my axis. About this axis, it's going to rotate, okay?
Okay, sir.
Let's say this point is A and the end point is B. Now, the moment I am rotating it, right? Let's say I'm rotating through an angle 30 degrees.
Okay.
Now, tell me one thing. Here is point A, here is point B, right?
Yes, sir.
Now it has moved to a new position, correct?
Right.
Now, can you tell me whether displacements covered by A and B are same in this rotation?
No.
No, right? Which covers less displacement, which covers more displacement? This is A, this is B.
A covers more, B covers less.
How come here?
Wait.
See here,
So,
I moved it from here to here. A is this much. Small
okay.
displacement. B has covered what?
A much longer one.
Larger displacement. Are you able to visualize?
Right.
Right?
Yes, sir.
See, yes or no? The mouth is opening wide, right? At the ends.
Correct.
compared to at the beginning? Yes or no?
Yes, sir.
Are you able to visualize?
Now got it, sir.
Really?
Really, sir.
Okay. So then do you understand displacements are not same? So in
Right.
rotational motion, displacement is different for different points. Are you clear?
Yes, sir.
So that's the reason we don't talk about linear displacement in rotational motion, correct?
Right.
But what is important in rotational motion? Angular displacement is same. For example, when I rotate this by 30 degrees, right? Or if I have to show it like this, I rotate this by 30 degrees. By what angle point A has moved?
30.
What about B, point B? This was the line, right? From here it has moved. So B also, when you connect it, the angle will be what?
Also 30.
30. Understood or not?
Yes, sir.
Displacements are different, but angular displacement is what?
Same.
Same. Angular displacement means theta. So that's why we talk about theta in case of rotational motion. Is it clear, Samuel?
Yes, sir.
Okay. So in rotational motion, we talk about what?
Angular displacement.
Theta. Similarly, linear velocities are different in translatory motion, right? Because unequal displacements are covered, therefore, in the same time, right? Suppose I move this by 30 degrees, A covers shorter distance, B covers what?
A longer distance.
Longer distance in the same time. So the velocity of B is what? It covers longer distance in the same time. So what is the velocity of B? If something covers longer distance in the same time, isn't it faster?
Yes, sir.
It is on the same body, but then when the body is rotating, different points cover different displacements with respect to time, correct?
Yes, sir.
That means they have different velocities. Do you agree to that?
Yes.
So velocities are different, but what is same? Angular velocity is same. What is
Right.
angular velocity? Omega, which is d theta by dt. That is same. That's why we talk in terms of angular velocity, or another name for this is angular frequency. Just give me a second. Is it clear, Samuel?
Yes, sir.
Okay. Similarly, acceleration for every particle will be different because velocity is different, right? For every particle,
Yes, sir.
every point on the rigid body.
Mhm.
So acceleration will be different for different points in case of rotational motion. Therefore, what is more relevant is angular acceleration, which we denote by alpha. It's called angular acceleration. And what is angular acceleration? Rate of change of angular velocity with respect to time. So I'm telling you the equivalence, okay, in both.
Right.
Just like how you have velocity is equal to ds by dt here, angular velocity will be what? D theta by dt.
dt.
The way you have acceleration is dv by dt, here you will have what?
Alpha is d omega by dt.
All right. What is omega?
Omega represents angular acceleration. Wait. Not angular acceleration. Angular acceleration is alpha. Omega was angular velocity.
Yeah, we must be very clear about that. Should I write all these? Theta is angular displacement. Omega is angular velocity or also called angular frequency.
Right.
Alpha is angular acceleration. Okay.
Yes, sir.
Then what is momentum?
Rho.
Not rho, P. Simple P. All right. So what is momentum?
P equals to mv.
Mass into velocity, correct?
Right.
Here you have a term called, obviously here also if you see, because velocity is changing for different points on the same rigid body in rotational motion,
Angular momentum.
momentum will also be changing for every point.
Correct.
So we talk about a term called angular momentum for the rigid body. It is denoted by the symbol L, angular momentum, and that's going to be equal to, see here, in place of V, what do I substitute here? What do I write here? What is an equivalent of V here in rotational motion? See, the matchups are here, right?
Correct.
So that's the way you will know new thing from something which you already know, all right? So
Correct.
wherever you used to use velocity, linear velocity in translatory motion, in rotational motion, you will use what?
Omega.
Angular velocity, correct?
Right.
So here you have V here. So what do you use here?
Omega, d omega by, just omega, omega by t.
Why T? Where is T here in this formula? I'm saying it is match up, right?
Right.
So here you have only mass into velocity, right?
Hmm.
So in place of mass, you should write something. In place of velocity, you're writing angular velocity. Is that clear?
Okay.
Where is time coming in? Clear or not?
Yes.
Okay. So only thing is you should know what you should write in place of mass, right? We have already discussed inertia is because of what? Inertia in linear motion is because of what?
Mass.
Mass. Very good. More the mass, more the inertia. Do you remember?
Right.
Right. Here we will talk about a term called moment of inertia denoted by I. So which is the reason for inertia in rotational motion. Okay. So I'll give a brief intro to moment of inertia. Just like mass was exclusively deciding the amount of inertia a body has. In
Right.
rotational motion also mass is important, right? Mass decides the amount of inertia the body has. More the mass,
More than us, yeah.
more the inertia. Very good. Now, in addition to that, because the body is rotating, one more factor also comes into picture. Okay. So let me give you an idea. That is the distance of that mass from the axis of rotation. So let's say this is the axis of rotation. Okay. Now this is the axis about which the mass is going to rotate. Okay.
Yes.
Now, greater this mass, greater is the moment of inertia, greater is the inertia, correct?
Yes.
Similarly, one more factor. See, in linear motion, this factor was not there because body was not rotating. But in rotational motion, this factor is there. What is our distance of that mass from the, what is this line called?
Axis of rotation.
Axis of rotation. So, in fact, your inertia depends on the square of that. So, your inertia is a function of both mass and also what?
I'm R squared.
R square. So depending on the shapes of the body, the moment of inertia is derived. Okay.
Yes.
I'll probably derive it for one or two cases so that you will understand. Okay. So what you have to understand is wherever mass is being used in translatory motion, an equal matchup is what? In rotational motion, I.
Right. Right.
Mass was the inertia in linear motion. I, which is called as what?
I.
No. What is I
I
called?
is called as moment of inertia.
Moment of inertia is for rotational motion.
Right.
And you can understand it is going to be a function of not only mass, but also what? Also what?
Angular velocity.
Not only depends on mass, but also what?
Also depends on what inertia. Wait. R, radius.
Not radius. What is R?
R square.
No. What is R? Distance of this mass from the axis of rotation. I'm giving the matchups because suddenly if I drop these formulae, right, for you, it may all look Greek and Latin, correct?
Right.
That's why I'm comparing, right? So that it becomes easier. You will know unknown things from something which you already know, correct?
Yes.
Right. Now next thing. So here we use force, right? We talk about force.
Listen.
F is equal to dp by dt, which is also equal to what?
MA.
Ma. Here the equivalent is what we call as rotational force. What is another name for rotational force? Torque. So can you tell me what is torque going to be?
R into F.
R into F is one way of writing it. Okay, we are going to talk about that. But now I want you to tell based on the matchup.
Oh, okay. M is there, so I.
Yes.
And acceleration is there, so we have omega.
What the acceleration is?
Acceleration is alpha, son.
No, first tell me 5 times.
I.
Angular velocity is omega. Angular acceleration is alpha. Angular displacement is theta. Because these are like standard symbols, right? Come on, quick. All the four you tell me. Theta, omega, alpha, L.
Only the symbols, sir.
Tell me the word and the symbol. Yeah.
Okay. Angular displacement is theta, angular velocity is omega, and angular acceleration is alpha.
Look at me and tell. Not from a book.
Angular displacement is theta, angular velocity is omega, angular acceleration is alpha.
Angular momentum.
Angular momentum is
L.
L. Okay.
Okay, go ahead. Again, repeat.
Angular displacement is theta, angular velocity is omega, angular acceleration is alpha, angular momentum is L.
All
Angular
right.
displacement, angular displacement, done, sir.
No, one more. No, go ahead.
Okay. Angular displacement is theta, angular velocity is omega, angular acceleration is alpha, and angular momentum is L.
Yes. Going forward, even you can say, rotational force, torque is tau.
Right.
Right. Okay. Okay. Now see here. Now tell me, you were doing the matchups, right? Go ahead. Now tell me.
I alpha.
I alpha is one way of writing it, which is a matchup for MA. What is it for dp by dt?
What's that?
See, you have one more formula, right? F is equal to what?
dp by dt.
For that you tell me. What is the matchup? What is P?
Momentum.
What is the equivalent for this here?
MV, so L.
No.
L.
Angular momentum. So
L.
you have dp by dt here. So what should you have here?
So L is one thing divided by.
No, you just look into this formula and try to equate it, right? F is
Right.
dp by dt. What will be torque? See here, dp by dt means what? Differentiation of linear momentum with respect to time. What will this be? This will be nothing but differentiation of angular momentum with respect to time, right?
Right.
And you need to get the matchups, right?
Right.
So what is torque equal to? Tell me again.
dp by dt.
Not dp by dt.
dl by dt, change in angular momentum.
Rate of change of angular momentum with respect to time. Another way of writing it is what you said earlier. What is it?
R into F.
R into F, forget it. Right now we'll not.
I alpha.
I alpha, yes. Okay. These are kind of fundamental. All right.
Right.
Okay, next we'll go to kinetic energy. All right.
Right.
So what is kinetic energy in linear motion? How do you write it?
Half mv squared or p squared by 2m.
Yeah, come again.
Half mv squared or p squared by 2m.
Very good. Okay, now
No
also
notation.
you call it kinetic energy. Only difference is you call it as rotational kinetic energy. So can you tell me what would it be?
Half
Yeah.
m is momentum, so L.
M is what?
Angular displacement.
M is angular displacement. What is M?
Angular momentum L.
M is, first tell me the matchup for this half mv square. What is M in that formula?
mv. P equals to mv. That
No, tell me one thing. Just answer my question, what I'm asking you. What is this half? What is this?
m.
What is M? What is M?
M is mass. M is mass.
Mass, you have not told that. What is V?
Velocity.
Right. What is equivalent? Now tell me the equivalent.
Angular momentum L.
Is angular momentum L equivalent for what? Okay, tell me this 5 times. The equivalent of mass in rotational motion is moment of inertia, I. We
Sorry,
have,
sorry.
we have discussed this, right?
Right.
Go ahead. What right? Go ahead. Tell this. The equivalent of, tell me,
The equivalent of
mass
mass
in linear motion
in linear motion
is
is
moment of inertia in rotational motion.
the equivalent of mass in linear motion is moment of inertia and rotational motion.
What is moment of inertia symbol? Tell that also.
I.
I. Okay, please go ahead. Repeat.
The equivalent of mass in linear motion
Is
moment of inertia and rotational motion, which is I.
yes. Okay. Again.
The equivalent of mass in linear motion is moment of inertia I in rotational motion.
Okay. Now tell me the equivalent of V, velocity.
Omega.
Yes. Correct. So what will be the formula in rotational kinetic? What will be the rotational kinetic energy?
Half I omega squared.
Very good. Are you getting it now?
Listen.
Because otherwise, all these formula will look like, they have jumped from somewhere. Correct?
Yes, sir.
Because not able to remember the formula is one of the most important challenges that students face in this chapter. That's the reason I'm spending time on what each one means. Okay.
Understood, sir.
Okay. Now next, come on. Now what is look at the board. What is kinetic energy?
Half mv
Half
squared
mv square. What is the other one?
p squared by 2m.
Yes, p square by 2m. Right. Now focus on this.
Yeah.
So what is your p?
P is momentum.
Yeah. Now onwards you will call it as linear momentum. Correct.
Okay.
What is m?
Mass.
Correct. Now tell me the equivalent in rotational motion. What is the equivalent of linear
P.
momentum?
Oh.
Don't refer. You should be able to tell. See, a linear velocity, the equivalent was angular velocity. Linear acceleration, the equivalent was angular acceleration.
Angular
Momentum,
momentum.
what would it be?
Angular momentum L. L squared.
Ah,
Right. L squared by 2 remains as it is. So does the 2 remain?
Yeah, of course it does. So don't worry about that. Tell me about mass. You're not remembering for mass. Tell me 5 times. Tell me again. The equivalent of mass in linear motion is moment of inertia I in rotational motion. Tell this 5 times.
The equivalent of mass in linear motion is moment of inertia and rotational motion. Equivalent of mass in linear motion is moment of inertia and rotational motion.
Moment of inertia I. Tell that. Tell that. Otherwise,
Moment of inertia and rotational motion.
go slow. Again.
The equivalent of mass in linear motion is moment of inertia I at rotational motion. The
Is that clear?
equivalent of,
Yeah,
yes,
go ahead. Go ahead.
the equivalent of the equivalent of mass in linear motion is moment of inertia I in rotational motion.
Yeah. Okay. So now can you tell me the matchup? So what is kinetic in a rotation?
L squared by 2I.
L square by 2I. Are you understanding now?
Yes, sir.
So if you do not know these, then you'll have to just skip the chapter and move on. And that will be a major portion in your competitive exam also. And also you'll have good amount of questions coming in your 11th CBSE, correct?
Yes, sir.
That's why most students don't learn this chapter because they don't know this. They're not spend time on this.
Right.
It is important to spend time, right?
Yes, sir.
Okay. So all this formula must be in your fingertips, correct?
Understand, sir.
Tomorrow when I ask you what is tau, you should say without thinking I or dl by dt. Clear?
Yes, sir.
Okay. Now the other related ones come from your trigonometry. Of course, less significant than what we have discussed so far, but still important. So here you would have learned the very first exercise in trigonometry. If you see, even before you started learning the formulae, if a particle moves from, let's say, A to B along this curved path, which is part of a circle, right? You call it as a sector of a circle, correct?
Right.
Let's say this is the radius and this is the length it has covered. Then you would have learned it as L is equal to R theta, correct?
Yes, sir.
Now, if you differentiate this on both sides, what would you get? dl by dt. That's like displacement, rate of change of displacement with respect to time. So that will be your velocity. R into d theta by dt, that will be your omega. So another formula which connects V and omega is what? V is equal to
R omega.
R omega. Similarly, if you differentiate this once more, right, you get acceleration. So acceleration is equal to, if you differentiate on the right side, right, d omega by dt, you will get alpha. So A is equal to R alpha.
Yes, sir.
Similarly, torque is given by R vector cross F vector. Cross refers to cross product.
Or two vectors.
I have told you, right? There are two ways in which you can multiply vectors. One is dot product, like we have seen, right? Work done is equal to force vector dot displacement. Do you remember?
Yes, sir.
What is it called?
Dot product.
Dot product, or it is also called scalar product.
Scalar.
Why it is called scalar product? Because the outcome is a scalar. Work done is what?
Work done is a scalar quantity.
Scalar quantity. Force and displacements are of course vectors, but when you do a dot product on them, you get the result as a scalar. That's why dot product is called
Scalar product.
scalar product. There is another way in which you multiply two vectors, in which case you are going to get the result as a vector. So that is called what?
Cross product.
Cross product, or it's also called what product?
Vector product.
Vector product. Very good. So if you take magnitude, right? What is A vector cross B vector? Do you remember? What was A vector dot B vector?
AB cos theta.
What is A vector cross B vector?
AB sin theta.
AB sin theta, right? So here vector product, when I do, it becomes RF
Sin theta.
sin theta. Is that clear? And if theta is 90, then sin 90 becomes 1. That's when what you, the formula you told becomes valid. Tau is equal to what? RF.
Right, sir.
But ideally the definition is R cross F.
Right.
This is also important, but then this list of formulae are very, very important. Okay.
Yes.
Okay, now going forward, we'll continue, right? When acceleration is constant, it's called uniform accelerated motion. We saw it in the very first class, physics class, correct?
Right.
What are the equations you know?
V equals to U plus AT.
Right.
S equals to UT plus half AT squared. And then V squared is minus U squared equals to 2AS. So V squared is equal to U squared plus 2 minus plus 2AS.
Correct. No problem. Perfect. Now you're going to do the matchup. So here, what should be constant?
Acceleration.
That is in linear motion. I am talking about rotational motion.
Oh. U.
Again, you are answering without putting us sparing a thought. What is the matchup for acceleration in rotational motion?
Angular acceleration.
Yeah, so what should be constant now in rotational motion?
Angular acceleration.
Yes, okay. So when angular acceleration is constant, so wherever V is used, what are you going to use?
Sorry, sir, come again.
Without looking at the table in the notes, tell me. So what is the equivalent of velocity in rotational motion?
Omega.
Good, angular velocity. So you can call it as final angular velocity, and U is initial velocity in linear motion. So here you will call it as what?
Omega I.
Right.
Initial angular velocity.
Very good, very good. And what is in place of A? Here you have V is equal to U plus AT, right? In place of V, I am writing omega F. In place of U, I am writing omega I. In place of A, what would I write?
Alpha.
Good. So you have this equation. Is it clear?
Right.
If I don't give the background and suddenly write this equation, you may wonder it's a new equation, correct? Brand new equation, and you'll not be able to connect to it, right?
Right, sir.
Now tell me, S is equal to UT plus half AT square. What will be the equivalent in rotational motion?
S is displacement.
Yeah.
So we require angular displacement.
Tell me. Go ahead. Good.
Angular displacement is theta, the coefficient.
Symbol.
Yeah. Omega I.
Good.
Omega IT.
Very good.
Plus half alpha t squared.
Very good. So these you must remember, okay? I mean, first time we are relating it and generating the equation. In future, you should start remembering it directly, right?
Yes, sir.
Okay, now tell me my last equation.
Omega f squared, because it is final velocity, is equal to omega I squared plus 2 alpha theta.
Very good. See, here a brand new equation you are able to tell on your own just because of the matchup, correct? Because you're able to relate to them, correct?
Yes, sir.
That's very, very important. That's why this comparison is extremely important.
Right, sir.
Okay. Clear so far, Samuel? Any doubts?
No, sir.
Okay, good. Now, next. Next is we had learned about law of conservation of linear momentum. In previous class, we had also solved questions on this.
Right.
What is law of conservation of linear momentum? Tell me, Samuel.
If the net external force which acts on it acts on the system of a body which remains if it remains zero, then the momentum system will remain constant.
Very good, excellent. So if external
Yes.
if external force is zero, then we know that external force is given by what formula?
F-E-X-T.
No, what formula? What is the formula for a force? Immediately you should say dP by
dP by dt.
Here you're differentiating a quantity and it's becoming zero, then what is that quantity? What should that quantity be? You have learned in differentiation that if you differentiate a constant, you get what?
Zero.
Therefore, P must be a
Constant.
Therefore, P is a constant. In physics, we call it as being conserved. Conserved means it doesn't change. Is it
Right.
clear? What does it imply? It implies whenever external force acting on the system is zero,
Momentum gets conserved.
momentum gets conserved, which means
It remains constant.
that means whatever was initially the momentum, the final momentum will also be same of the
Right.
system.
No.
Clear?
Yes.
Okay. Now, what is the matchup in rotational motion? Can you tell me?
Or dP by dt, sir.
For this entire law, you have law of conservation of linear momentum, right? How
Yes.
would you have it in rotational motion?
Angular momentum is L. So
Yes.
L by T.
So
For
what will be this? What will be the
just for P.
law? What will it be? Law of conservation of what? In rotational motion.
Angular momentum.
That's all. So the law is law of conservation of angular momentum. And when can we apply this law?
When it is not constant. Angular momentum is constant.
Sorry. That's fine, but when will it happen?
When it is conserved, then angular momentum is conserved.
When will angular momentum be conserved? Don't say angular momentum is equal. Once again. You're just, beating the bush around this. Correct? I'm asking you when is angular momentum conserved? When angular momentums are equal. When are angular momentums equal? When angular momentum is conserved. You're just switching between those two answers. But when does that happen?
When it is constant.
That's what you just switch between the two. Very smart, right? But it doesn't help. See here, what is the condition here? When external force is zero, momentum is conserved. Yes or no? So what would be the condition for law of conservation of angular momentum?
If the net external force acting on a body is zero.
See here, you have to match up. The moment I talk about force, what is the equivalent of force in rotational motion? Go ahead, 3 times. Equivalent of force in linear motion is torque in rotational motion. Repeat that 3 times.
Equivalent of force in linear motion is torque in rotational motion. Equivalent of force in linear motion is torque.
Slowly, so that you observe, you don't simply tell it. As you tell every word, it is getting into your head. The idea of asking you to repeat is not some ritual.
Right.
I want it to get into your head, get drilled into your head, right? Go ahead. So say like that.
Equivalent of force in linear motion is torque in rotational motion.
Yes.
Equivalent of force in linear motion is torque in rotational motion. Equivalent of force in linear motion is torque in rotational motion.
Okay. So wherever you use F, here in rotation motion, what are you going to use?
Torque, tau.
So here, if external force is 0, your momentum is conserved, correct? Here, what would be the equivalent condition?
If torque is equal to 0.
If external torque is equal to 0, correct, Samuel?
Yes.
Then, what will be the formula for torque? Don't just tell RF, right? So we have seen 2 new formulae. What are they?
One was RF. But
no, RF is what you have been telling from the beginning today morning. What did you learn today?
I alpha.
I alpha. Very good. What else?
Then dl by dt.
Yes. Without referring to your notes, you must be able to tell by tomorrow. Okay. Fine. So tell me, ma'am, why is it dl by dt? Because if you see the equivalent matchups, right? dp by dt here. So what is the matchup for P? L, right?
Yeah.
So it is dl by dt. So this means dl by dt is 0. You are differentiating a quantity and it's becoming 0. Which quantity are you differentiating?
Differentiating L.
L. What is L?
Angular momentum.
Good. So what is conserved?
Angular momentum.
Angular momentum is conserved, right?
Right.
So I can write L is conserved.
So does that mean that Li is equal to LF?
Yes, absolutely. Good. So that's how you should start comparing and yes, good. So Li is equal to LF. Now one final thing on this, right? Now go to this formula Pi is equal to Pf. What do you mean by Pi? How do you find what is P? Momentum, right? What is momentum?
Mass into velocity.
Correct. So mass into, I'll put a summation because there may be many particles in the system.
Right.
So their individual velocities you need to multiply with mass and add them.
Right.
What is PF?
Sigma M UF.
Yeah, go ahead. Correct.
Sigma M UF.
UF. Or you can say VF or V, whatever. Final velocities. Is it clear?
Listen.
Now tell me the matchup for this condition.
L can be either L.
What is in place of mass in rotational motion?
Moment of inertia. Moment of inertia.
Very good.
Into angular velocity. So I omega.
Very good. Very good. Very good. Okay.
There also sigma, sir.
Yes, ma'am.
There also you should write sigma.
Yeah. Because you may have more number of particles. Suppose you have 3, because it's rigid body, right?
Correct.
We're not talking about a single particle, we're talking about group of particles.
Right.
So it is I, because see here, yeah, mass also could be different for different particles. So if you want, you can include Mi also here.
Right.
Only thing is, the masses will be same, right? Mass will not change.
Mhm.
So they stay same on both sides. That's all. But for
Yes.
individual particles, it will be different. So I into, come on here, what is it?
Omega I.
Very good. That's equal to,
Sigma IF omega F.
yes. So is this clear, Samuel?
Yes, sir.
This table is very, very important, right? Whatever I've given you here. So this is this table, entire thing what I have given, right? That's very, very important because that's how you can remember them, right?
Right.
Or else it will be completely new, correct?
Right.
So now with this, is it simpler to remember all these equations by using the matchup?
Yes, sir.
Okay. So I hope all of this you have noted down very clearly.
Noted down, sir.
Good, good, excellent. So now I'm going to talk a little bit about moment of inertia. Okay. So as I told you, there is a moment of inertia basically depends on what?
Mass.
See here, in linear motion, inertia was only because of mass.
Mm.
In rotational motion, I told you it is dependent on mass, but not only on mass, right? So what else?
I omega 0.
I'm only talking about I. Where is I omega coming here?
Okay.
Can I not show you? This is a rigid body. Let's say there is a
Axis
particle.
of rotation.
Huh? Okay, axis of rotation, fine.
R, the distance.
Ah, yes. So it will be what? Your moment of inertia will be m1 into, come on, squared of the distance, r1 square. Correct? Did we not discuss this?
Right.
Now let's
Yes.
say you have another mass m2, which is at a distance of r2 from the axis. Then it will
M1
be
R2 squared.
m2 r2 square. Correct? Like that, right? You have more particles, let's say. You have another particle m3 at a distance of r3, then what you will get? So your moment of inertia is sum of all these values, mr square values, correct?
Right.
But suppose if you have infinite number of particles, it is no longer sigma. This formula is valid only if there are finite number of particles. If there are finite number of particles, you can add them, correct?
Right.
If there are infinite number of particles, you cannot add them. What will you do?
Integrate them.
You will integrate, right? So you will integrate all these. So how do you do that? We are going to see, okay? For one or two bodies, I will show you. Rest of it, we can go by the list given in your textbook. So in your textbook, there is an entire table which you need to remember of the list of moment of inertia, right? We will do for one or two. Just to give you idea of, how it is done. Okay. Moment of inertia of a uniform rod of mass m and length L. About an axis passing through its center of mass and perpendicular to the rod. So we're going to find out the expression for moment of inertia of a uniform rod. What do you mean uniform rod? Mass distribution is constant. That means if the length of the rod is 10 meters, let's say the total mass is 10 kg, Each meter will have 1 kg mass, correct?
Right.
Equal distribution of mass. Then that is called uniform rod. Okay, now let's consider that. Let's say this is a uniform rod. So axis, where is the axis? The center of mass of the rod is at the center of the rod. Okay.
Okay.
Suppose the length of the rod is L. Right? Then the center of the rod, wherever the rod has a center, right? That becomes its center of mass as well.
Right.
And where is the axis? The axis passes through center of mass and it is perpendicular to the rod.
Right.
So how do you draw the axis? Axis is a line which is perpendicular to the rod. Is it clear?
Yes, sir.
And passing through this point, center of mass.
Right.
And about this line, the rod is rotating.
Okay.
Are you able to visualize this?
Yes.
Suppose this is the axis, the rod is rotating like this.
Right.
Okay, fine. Now we need to find out the moment of inertia for this. So how do we find? Using integration. Especially in 12th, you're going to learn a lot of integration. I'm sure you have done a few integration in your work by energy and other parts of physics.
Yes, sir.
So now we are going to see. I'll just tell you the procedure for 1 or 2 questions, okay? The rest of it, we will take it as a formula. So the condition is this. This is the procedure. So let us say a small mass, let me call it as dm, okay?
Right.
M is the total mass. Let capital M be the total mass of the capital M is the total mass of the rod. I am taking a small portion dm, which is having a width of dx, okay? And let us say the distance of it from the center of mass, let's say, is x, okay? Then can you tell me the small moment of inertia because of the small mass? See, a di represents small moment of inertia.
Right.
Only because of this mass which I have drawn here, right? How much would be the moment of inertia? Can you tell me? What is the mass of that mass? Mass of that portion.
dm by
I told you
dx.
it is dm.
Right. dm. Yeah.
Yeah. So the mass is dm. You know what is moment of inertia given by Samuel?
I.
I. What is it dependent on?
Mass.
It's
Generally.
only mass.
The distance r.
Yes. Square of the distance. Correct? Yes or no?
Yes, sir.
Yeah. So this mass, at what distance is it from the axis? Tell me. I've shown you that in the diagram.
X.
X. Very good. So what is the small moment of inertia going to be equal to?
dmx.
dm into?
X.
Did I not tell you it is proportional to the square of the distance? Is it not? Are you not doing r square every time?
So dmx squared.
dm into? Repeat.
dm into the square of the distance.
What is the distance?
The distance is x.
Yeah. So what is it? dm?
Into x squared.
X squared. Yeah, that's what I wanted you to repeat. Why are you not repeating?
So, but I told it after.
Huh?
But I'd already told it, no?
No, I couldn't hear it.
Oh.
If I ask you to repeat, you should repeat, right?
Okay.
Okay, di is equal to dm into x square, right? Okay. Is it clear to you?
Yes, sir.
Okay, now you have to write dm in terms of capital M, okay?
Right.
Now I told you it's a uniform rod, right? It's given that it's a uniform rod. That means suppose the length of the rod is 10 meters and suppose the total mass of the rod is 20 kg, and every meter will have how much kg?
1 kg.
No. I changed the question, right? I didn't ask the same question which I gave you, correct? The answer doesn't remain same. What is the length of the rod?
10 meters.
What is the mass, total mass?
20.
20 kg, isn't it? 20 kg for a distance of 10 meters. So I'm asking you, for every meter, what will be the mass?
1/2 to 0.5.
What? Listen. 10 meters, 20 kg, correct? 5 meters, how much it will be?
Divided 20. 20 by 5.
20 by 5. No, wake up. If you're feeling sleepy, just wash your face and come. Are you active? Are you concentrating, focused?
Yes, sir.
Yeah. Okay, I'll tell you in something which you like, okay? One full, length of Dairy Milk chocolate, 100 rupees. Half of that, how much would it cost?
50.
Yeah, of course, nobody is going to give you half of it, right? Okay, I'm just telling you, if you were supposed to get it right. Quarter of it, how much?
50 by 4.
50 by 4. Total is 100 rupees. Half of it is 50 rupees. Half of that is what? Quarter.
25. 25.
Correct?
Right.
So entire rod is 20 kg. 10 meters is 20 kg.
Correct.
I'm asking you half of it, 5 meters.
10 kg.
Now you understood, right?
Right.
Okay. So I have to always go back to dynamic. Okay. So what is 1 meter?
100 centimeter.
I'm asking you conversions. Huh?
No.
For 1 meter, how much is the mass?
Okay.
Remember, maybe you visualize Dairy Milk chocolate. Huh? Can answer this question. 10 meters, 20 kg. 1 meter, how much? I'm asking.
20 by 10, 2. 2.
Okay, good. Fine, that's all, Ram. That's all. So listen now, listen.
Listening.
For this much length, right? The total mass is M, total length is L. Is it clear?
Yes.
For this much, what is the mass? dm. What is the length?
X. dm by x.
So, won't the ratios be same? 20 divided by 10, 20
2.
kg divided by 10 meters. Will it not be same as 2 kg divided by 1 meter?
Correct.
So, the ratio here is, all this chocolate story is for getting this relationship. M divided by L is equal to dm divided by dx.
Right.
So this big length and big mass, M. So big mass divided by the big length is equal to the small mass divided by the small length. Because it's a uniform rod, the ratio will remain same. Is that clear?
Yes.
Okay. So did you get this?
Yes, sir.
Okay. So what is dm from this? Tell me.
So dm.
Just cross multiply.
So dm says what we have to find, right?
I'm asking you what is dm from this? Just you can look at the board and tell, no need to solve, right?
L by dxm.
Keep dm as it is. Dx you shift there. What do you get?
You cross multiply, you get dxm is equal to dmn.
Fine. Don't take L. M by L, let it be here only.
Okay.
Just asking you what is dm.
dxm.
What happened to that L? Is it there or not?
Divided by L. Divided by L.
Yes, that's what I'm asking. So dm is equal to, come on, tell me again.
dxm by L.
Or you can say m by L into dx. Clear? Yes or no?
Yes, sir.
Okay. Yeah, because you should know the procedure of how to get the moment of inertia. That's why we are spending this time. So dm, I am writing it as what?
M by L times dx.
Yeah. And there is also a
X squared.
okay, fine. So now this is a small amount of moment of inertia. Now I want the total moment of inertia, right?
Integrate.
M by L is a constant, so I can take it out of the integration.
Right.
I can consider this as x-axis.
Okay.
I can consider this as x-axis. I can consider this as y-axis. All right.
Right.
What will be this point? Origin, correct?
Origin, yes.
Right. Okay. What is the total length? L, right?
L.
No, 10 meters was for example, but here it is L, right?
L. That's what I said.
So how much will this be?
L by 2.
L by 2. Good. So what will be this point? If this represents x equal to 0, what will this represent? X equal to?
Sorry, sir, coming in.
This point which I'm circling here at the origin, it refers to x equal to 0, correct? What will this represent?
The end point.
That's fine. What is the value?
L by 2. L by 2.
L by 2, correct? So this will be x equal to L by 2. Is that clear to you?
Yes.
So if I integrate the limits, because I need to write the limits, right?
Right.
So I'm integrating from 0 to L by 2. If I do 0 to L by 2, am I getting full rod or half the rod?
Half the rod.
Half the rod. But I need the moment of inertia for the full rod. So shall I multiply by 2 here?
Yes.
So that I get it for the full rod. Got it?
Yes.
Okay. So the integration of di is I. So when I integrate di, I get total moment of inertia I. Did you understand why I multiplied 2?
Yes, sir. For the full rod.
Correct. What is the, I think I have told you, right? Integration, if you remember one formula, it is enough for your physics solving numericals at this point.
Yeah.
So what was that formula? I gave you only one formula. You don't remember that? Say this. Integration of x power n dx is equal to x power n plus 1 by n plus 1. Say that thrice.
Integration of x power n dx equals to x power n plus 1 by n plus 1. Integration of x power n dx equals to x power n plus 1 by n plus 1. Integration of x power n dx is equal to x to the power n plus 1 by n plus 1.
Got it? Okay. So now tell me, what is the integration of what is given here?
X squared dx.
So what is n in this question?
N is 2.
N is 2. So what will be the answer?
X cubed by 3.
Yes, very good. So what is the method? First you substitute upper limit, then the lower limit. Upper limit minus lower limit. So when you substitute x as L by 2, what do you get?
L by 2 whole cube by 3.
Very good, very good. So what is L by 2 whole cube?
L cubed by 8. But hold on. Wait, L cubed by 27 because of 3. Sorry.
20?
7.
Why 7? Huh?
27.
How 27?
3 cubes, sir.
Why did you do 3 cube? Are you supposed to do 3 cube?
Oh, sorry, N is 2.
What should you substitute for x?
L by 2. Okay.
The cube is for the L by 2, not for the 3, right?
Correct.
Minus lower limit is 0. Okay. Now tell me, what is it? L by 2 whole cube, what is it?
L cubed by 8.
8, right? And what else is also there?
8 into 3.
So there is no 27, 24. Anyways, you can cancel this 2 also here. So it becomes 4, right?
Yes.
And 1 L gets cancelled. So you don't have L cube, but what do you have?
L squared by 12.
Yes, very good. Therefore, the moment of inertia of the rod about an axis passing through its center of mass and perpendicular to it is given by 1 by 12 ml square. Clear?
Yes, sir.
That's all. Correct.
Excuse me, sir.
Yeah.
So could you repeat the definition of uniform rod once again?
Uniform rod means what? Mass is equally distributed. That's what I said. For example, if you have a 10 kg, 10 meter long rod weighing 20 kg,
Correct.
at every point, right, at every, say, every 1 meter, the weight will be 2 kg.
Correct.
It's not like it is fat in the middle, it is, it is thin in the extreme ends. No.
Right.
Uniform means?
The mass is equally distributed.
Mass is equally distributed. Is that clear to you?
Yes.
That's why we are able to do this. M by M is equal to dm by dx.
Yes, sir.
Okay. Did you understand the process, Samuel?
Understood, sir.
Good. Okay. Now, let's do it for one more diagram or one more shape. And then for the rest of it, I will give you a list, okay? Which you need to remember. Anyways, you can derive it also. If you're interested, you can go ahead and derive it. Mostly, the tougher derivations, not tougher in general, lengthier derivations. These are very simple ones. The lengthier ones, if you see, especially for a sphere or for a cylinder, all that will be more important in JEE, not in your CET. So if you're more keen, then you can go ahead and look at those derivations, right?
Right.
But otherwise, mostly for CET, simple derivations as well as for your CBSE, right? Simple derivations and remembering those results will be more important. Clear?
Yes, sir.
Yeah. One second. Any doubts in this?
No, sir.
Okay. Now, one more we'll do, and then we'll look into the table, and then we will do a few questions. Okay, Samuel?
Yes, sir.
Yeah. This is one of the important chapters. We are spending more time on this. All right.
Yes, sir.
But today itself revise the chapter.
Okay, sir.
Or else it's volatile, right? Within 24 hours, you have to revise it thoroughly.
Right, sir.
Okay, now let's find out moment of inertia. Circular ring. Of mass M. And radius R. About an axis. Passing through center of mass and perpendicular to the plane of the ring. We're going to find out the moment of inertia of a circular ring of mass M and radius R about an axis through its center of mass and perpendicular to the plane of the ring.
Right.
Let's consider this ring. Okay. What is the mass of the ring? M. Because
Right.
I'm drawing it in 3-dimension, it looks like an ellipse in 2-dimension, correct?
Yes, sir.
But it actually is a circle, right?
Yes, sir.
So what is the radius of the circle? R. And where is the axis? Perpendicular to this. Are you able to visualize?
Right, sir.
It is rotating about this axis. Clear, Samuel?
Yes.
Okay. Now, so how do you do? Once again, you take a very small portion. Let's say the mass of the small portion is dm. Let's say the length of the small portion is dx. Then this is also uniform circular ring. I can also mention this word, uniform. What do you mean by uniform, Samuel?
Where mass is equally distributed.
Yes, that means any length. Let's say you take 1 meter, the next 1 meter you take, the mass will be what? Equal for those.
Right.
Yeah, okay. So what can I write? The mass divided by the total length will be equal to what? The small mass divided by the small length. Correct or not?
Yes.
Yes. In this case, can you tell me what is going to be the total length? When I refer to total length, can you look at the diagram and tell me what it is?
Referring to L in this case.
Correct. But what is this figure? What is this shape?
It's a circular ring.
Circular ring, right? So when I say the total length, what does it refer to? Do you know what is going to be the total length? You've learned it from lower classes, probably from 8th or 7th.
Circumference.
Circumference, yes. What is circumference of a circle?
2 pi r square.
2 pi r square?
2 pi r, sir.
2 pi r, right? Okay. So L is equal to 2 pi r. Is it clear to you? Knowing
Yes.
this avoids integration, okay?
Right.
If you do not know, you have to do it, right? So I can write m divided by 2 pi r is equal to dm by dx. So what is dm equal to? Cross multiply.
Divided by 2 pi r.
Okay. So now,
So now, sir, we don't need to do integration, right?
no. You will write integration formula, but then you don't have to do integration because it will be a very simple stuff to do.
Right.
I'll tell you. So the small moment of inertia for this di will be equal to, can you tell me what is going to be the small moment of inertia because of the small mass? What is moment of inertia definition?
It depends entirely on mass.
It depends entirely on mass.
It depends on mass.
And what else? Repeat. Moment of inertia depends on mass, or moment of inertia is a product of mass and r square. Tell it 5 times.
Moment of inertia depends on mass, or it is a product of mass and r squared. M into r squared.
And what is r?
The distance.
Distance, what distance? Distance between your house and college?
No, the distance between dx and the center of mass.
Not center of mass, not necessarily. Axis of rotation. In this case, it's becoming the center of mass because the axis of rotation is also there. But in general, what is dx? Not dx. What is that r?
R is the distance between dx and the center of the axis of rotation.
That mass and the
Center of axis.
don't say center. Not center.
Axis of rotation.
Axis of rotation is correct. Okay. Now tell me 3 times. Moment of inertia is the product of.
Moment of inertia is the product of mr squared. Moment of inertia is product of mr squared. Moment of inertia is product of mr squared.
Okay, tell me what is R 3 times. Don't say R is the radius, huh? Tell me what is R in general.
R is the distance between dx and the
Now, the distance between the mass in general.
sorry. R is the distance between the mass and the axis of rotation. R is distance of mass. Sorry, R is the distance between mass and axis of rotation. R is the distance between mass and axis of rotation.
Good, good. Now tell me, what is your DI? Small amount of moment of inertia created by this part, small mass. What is moment of inertia? Moment I say moment of inertia, what should come into your mind? Come on, what comes to your mind?
I is equal to R omega. That's the formula. Wait.
No, I think I'll start teaching something else for you. Huh? I'll forget mine. Where is R omega? Huh? Don't say something which comes to your mouth. Think. What is I? I'll make you repeat.
I is moment of inertia.
So what is it? What is it equal to? What is it a product of?
Mass mr squared.
Correct. So let's think and tell me where is the mass? What is the mass here? Because if I keep teaching and moving on, what is the point? You'll not bother to go through, right? So that's why I'm making you say this. Come on, tell me.
dm into dm into r squared.
Because this distance is also r. Okay. Yes or no, Samuel? Where did r omega come in? Out of the blue? Okay. So it is what dm into, come on.
R squared.
And what is dm? What is dm? We have got it here, right?
M by 2 pi r dx. So d into, sorry, m by 2 pi r dx into r squared. R squared into dx.
Got it. So what does this become? R and R gets cancelled, right? So what do you have?
M by 2 pi r into dx.
Correct. So di is equal to m by 2 pi into r into dx, correct?
Yeah.
Now you're going to find the total moment of inertia. What do you do?
Multiply by 2.
Okay, small value, how do you get a bigger, larger value in continuous distribution? Integrate, right?
Yeah. So you take the constant out.
Yeah, what are the constants here?
M by 2 pi.
M by 2 pi is a constant. Even r is a constant for every point. Wherever this mass is, what is its distance?
R.
Correct? So r is also a constant. I take r also outside. So only
dx.
Right? So this is a very simple integration. That means, I'm adding all these distances. If I add all these distances, what do I get? Dx, 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 all these distances, what do I get?
di.
I add up all these distances. What will I end up getting?
dm.
Distance, if I add, will I get dm? Dm is mass. I'm asking you, what will I get if I add these small distances?
The entire moment of inertia.
No, we are not even talking. Listen to the question clearly and then. I'm adding all the distances which make up the circle.
Okay.
Will I not get the circumference of the circle if I add all the distances which make up the circle?
Let's see.
Yes, Samuel?
Yes.
Yeah. So if I add all these distances, what will I get?
Circumference of the circle.
So integration is nothing but adding all those values. How many additions you have to do? Infinite number of additions. That's why you call it as integration, not summation. Correct?
Right.
Okay. So now mr divided by 2 pi is there. So if I add all these dx values, what am I going to get? Come on, tell me.
Circumference of the circle.
Which is nothing but
2 pi r.
So that's why I said no integration is required, because it's logic, right? You add all those values, you're going to get 2 pi r.
So you get MR squared.
Yes.
So,
So in case of a ring, it is simply total m into r square. In case of a rod, what was it?
in case of rod was 1 by 12 ml
1 by
square.
12 ml square, correct? So like that, for different shapes, you will have different values. So can you take it down and let me know if you have any doubts?
No doubt, sir.
No doubts? Yeah. Just go through them for a minute and tell me if you're clear. Okay. Now I'm going to just give you a list of different shapes and their moment of inertia. Shapes with the axis and the moment of inertia. Okay. So first one, as we had seen, rod, correct? It is incomplete if I don't mention the where the axis is. So axis passes through the center. I'm sorry, I'm drawing it for the ring. Okay. So first let's do it for the ring. So we just derived Samuel. So what is the moment of inertia of a ring?
I is equal to capital MR into capital R square.
Very good, very good. Where m is the mass of the ring.
R is distance between mass and axis of rotation.
Correct. In this case, it becomes the radius of the ring. Next.
Then we have for the rod.
Rod. Yes.
Just a minute.
Let m be the mass of the rod. Let L be the length of the rod. So axis is passing through the center of mass and is perpendicular. So what is the moment of inertia of the rod in this case?
1 by 12 ml squared.
Yes. Okay. Now let me also give you a few more. Disc. Again, axis is passing through the center of mass. The mass of this is capital M. And let's say the radius is capital R. So you understand the difference between a ring and a disc, right?
Right. Yes.
So what is the moment of inertia going to be?
MR squared by 2.
Yeah, it is mr square by 2. Do you
See?
have the list with you from the textbook?
Yes, sir. But in that there are 2 cases for circular disc.
See here, I can generate several cases for everything. Okay. See here, I'll generate a few more cases, but I'm just giving you the general case right now. So this is case 1, okay?
Yes.
Where it's perpendicular, okay?
Okay, sir.
For example, I can have for the ring itself, I can have 2 or 3 more. I'll show you all the variations also, which is also important for your
Competitive
as well as for your boards, because it's mentioned in your text also, right?
Yes, sir.
I'll give you the different cases for ring, okay? So this is your ring sample. And the original one was passing through the
Center of
mass and perpendicular, correct?
Right.
I can have an axis which is tangential
Right.
and perpendicular to the ring. If I change my axis, right, do you think moment of inertia will change or not?
It will change.
It will change. So what is it going to be in this case? Another mr square will get added up.
So mr squared by 4.
No, no. For a ring we are talking about, it will be mr square. I told another mr square will get added up.
Mr squared by 2.
Another mr square
2
will
mr
get
squared. 2 mr squared. Sorry, sir.
For a ring. Okay. I'll show you one more. I'll show you probably two more for ring. Okay.
Okay.
Of course, there are derivations for this. There are logics behind this. I'll talk about the logics a little later, but at least you can remember them. Okay. I'll have to teach you two theorems to derive these. Okay. You don't have to use integration, but there are two theorems called parallel axis theorem and perpendicular axis theorem.
So, but for me, but in the exam it had come for physics exam, but that was out of syllabus.
That's fine. So that's why, that's why I did not teach you that.
Right.
I'm just giving you the values.
Okay.
But point is, your competitive examination will not say, that.
Correct.
Right.
Right.
So if you can use parallel axis and perpendicular axis for solving it quickly. But if you don't resort to that, then you have to resort to the original integration method.
Right, sir.
That we can't say it's out of syllabus, correct?
Yeah.
So what happens is that makes it challenging. Rather, we could learn that parallel axis and perpendicular axis theory, although it's removed from the latest NCERT syllabus, correct?
Yes.
Yeah. But all these values we need to remember. So now if I'm going to draw it here, this is the third case. So this will be mr square by 2, okay?
This is
For a ring. Okay, Samuel?
Yes, sir.
One final case.
For ring, sir.
For ring.
Okay.
So one method is you can remember all these, okay? Another method is to be able to derive it, but derivation you'll be able to do only with those theorems, okay? Presently, because you're having your exams right now, I'm not getting into that theorem, okay?
Right.
But anyways, when we review the chapter, we'll do the theorem. So for competitive, it will be helpful.
Right, sir.
I'm sure although it was not part of the syllabus, they would have done theorems, right?
Theorem they just did, sir.
Yeah, that much is
said, in the exam, they had mentioned on question based on this. They had said using the theorem of parallel axis, calculate moment of inertia for
correct.
That, for another case, not in ring.
Correct.
For cylinder, hollow cylinder.
Good. Okay, ma. So this is the last case. So in this case, how is it run? It is going to be tangential, but along the plane, correct?
Right.
So here it is going to be 3 mr square by 2. These are the 4 cases for
Ring.
Clear?
Yes.
Usually questions will circle around these 4 cases.
Right.
Clear, right?
Yes.
If nothing is told about the axis, then it means it is the first one, standard one.
Yes, sir.
Okay. Next, we will look at similar ones for rod as well. Okay. For the rod, if you see, at least one variation, if you see, that's enough in rod. Because rest of it is similar. So instead of the axis being here, the axis being at one of the corners.
Right.
So in this case, the moment of inertia will be ml square by 3. I don't require these cases because these cases will be repetition of this.
Right.
Because in case of a rod, it doesn't matter. If I draw it like this also, it is no different from the first case. So answer will be ml square by 12. So it's not a new case. Similarly, if I draw a rod and at one of the ends, if I draw it like this, then it is no different from ml square by 3.
Right.
But in case of a circle, a ring or disc, it makes a difference because of its shape.
Correct.
Okay. Now let's look at similar to ring. We are going to look at for discs. For a disc, what is it going to be? So first case is very similar to what we did for ring, right?
So two MR square gets added. One more MR square gets added.
One more mr square gets added is the right answer. Okay. Already it is half mr square. With that, one more mr square gets added. The answer will be 3 by 2 mr square.
3 by 2 MR square. Correct.
Now I change the plane. Now it is passing through the center of mass, but then it is on the plane itself, the axis.
Right.
So if it is so, it will be half of what it was before. So earlier it was mr square by 2, correct?
Yeah.
Now it will be half of that. That's something that's you can remember it as a trick or a short technique to remember. So here also you can ring. For ring, if you see, it was mr square. The moment you shift it on the plane, it is what? Half of it.
Right.
Okay. Now last. Disk. Your moment of inertia, your axis is not passing the center of mass, but it is a tangent. Correct?
Right.
So what will it be? It will be mr square more than this value.
Right.
These are ideas which will help you get to the answer fast, even if you forget. So what was this answer? mr square by 4, right?
Yes.
Previous one. So to get this one, you have to add another mr square to it. So your answer will become
5 MR square by 4.
exactly. So as far as your exams are concerned, the questions will revolve around these variations. You will not have usually more variations than these for a given shape. All right. Any doubts?
And just go through, sir.
Yeah. Then hollow cylinder. Or you call it as a hoop. Okay. This is basically a hollow cylinder.
Yes.
The axis is passing through the center of mass. So moment of inertia is going to be once again half mr square. All right. Now here you can only have one variation, which is usually a question in your CET or your CBSE. This was the original axis, right? Now this is rotating about the tangential axis. So to get this, what do you do? I have told you a trick, right? What is it? Add another mr square to it. So what do you get?
3 mr squared by 2.
That's all. So usually these are the two variations which are asked.
Right.
Then you have the next shape. I can call it as a hollow sphere. For a hollow sphere, if you see, let me take the sphere. Okay, ma'am? The moment of inertia of coordinate axis passing through center of mass.
Right.
Moment of inertia will be equal to 2 by 3 mr square.
Yes.
For each of these derivations are there, but then those are not critical for your CBSE or even for your CET.
Yes.
Now let's say you have a sphere. The other variation is what? Not the axis passing through center of mass, but what? A tangential axis, right?
Right.
So how do you find the moment of inertia? I told you to add an mr square. So it becomes, usually these two variations are going to be given in the text as well as what you may need to know. Clear?
Yes.
Similarly, solid sphere. Solid sphere means the complete volume is filled by material, right?
Correct.
Once again, there are only two variations which are important. So one is axis passing through center of mass. So what will be the moment of inertia? In case of solid sphere?
2 by 5 mr squared.
Yes. So now this time it is not through the center of mass, it's through the axis passing through tangent. What have I told you? How to get it quickly?
Half of that.
The mr square.
Sorry, sir.
Yeah. You want to tell something?
Now, how do you get 7 by 5 mr squared?
You add another mr square. This distance is r, right?
Okay.
Here also you did the same.
Right.
Basically, that comes from a theorem called parallel axis theorem. But anyways, that's not in syllabus. That's why I'm not discussing that. But I'm just giving you a hint.
Okay. Sir.
Okay. Any doubts, Samuel?
No, sir.
Okay. So please read through this chapter. Give it a good amount of importance. So go through all these theory part. I'll give you the formula for center of mass. We are going to do a couple of questions on this because you have those equations. Then information about cross product is given. Already we have discussed that. AB sine theta, right? So go through that also.
Excuse me, sir.
Yeah.
So you're going to be sending an assignment on this?
Yeah, I'm going to send an assignment. I'm going to solve at least a few questions right now. I'm also going to send an assignment on this.
Okay, sir.
Okay, ma'am?
Yeah.
So go through. So first assignment is go through these things, right? We have already discussed like torque external is 0, then dl by 0, dl by dt is what?
0.
L is constant, right?
Mm-hmm.
There is a sum based on that. I'll tell you how to do this as well. Okay. So did you studied in ICC or CBSE, Samuel?
CBSE, sir.
10th also, right? Okay. So your kinetic energy, I told you it's what? Half I omega square, correct?
Oh.
Okay, this is what I was talking about, right? So
Yes.
a ring, it's mr square. For a ring, if it's going through the diameter, it's mr square by 2. For a rod, it is ml square by 12. The other case is not presented here, but I have given you. So here, if the disk is passing through center of mass, mr square by 2. If it's on the plane, it is mr square by 4. For a
Yes.
hoop or a cylinder, hollow cylinder, mr square. And for a solid cylinder, it is going to be mr square by 2. So I think, did we miss something here? Hama. So point is, the result we presented here is not for a hollow cylinder. For a hollow cylinder, it follows same as that of ring. Okay.
Okay, sir.
So what I have given you is for solid cylinder. For a hoop or a hollow cylinder, it is same as that of what? Ring.
Right.
Keep in mind. And solid cylinder, it will be similar to disc. Okay,
Right.
then solid sphere, 2 by 5 mr square. For a hollow sphere also I have provided you, which is 2 by 3 mr square, correct?
Yes, sir.
And you have all these three equations, right?
Yes, sir.
So here the equations will be what? Omega is equal to
Alpha t
omega
plus.
naught plus alpha t. Got it?
Oh.
Derivation is done using integration that you can go through.
Yes.
So all the three equations are given, right? Which we had seen. So theta minus theta naught, is there because theta naught is the initial displacement. That's
Yes, sir.
okay. So all these numericals are important. I want you to go through these numericals as well. All right. So till here, till page number 27, right? I want you to go through.
Okay, sir.
Okay, ma?
Now.
Whatever we have taught, you should be able to go through them. But anyways, at least 2-3 questions from your textbook I will solve.
Okay, sir.
So that you know you are clear. Okay, first I'll discuss the concept of center of mass for you. Okay. So far we have been discussing about center of mass, right? Several times, right? We mentioned this word. What do you understand from this word center of mass?
In a rigid body, it can either be inside the rigid body or outside the rigid body at which the whole mass is said to be concentrated.
Very good, right? So the idea behind this is this, right? Suppose, let's say this is a rigid body, okay? Yes, Samuel?
Yes, I can see.
Okay. Now, normally if I apply force at different points, I'm applying force at 5 different points, correct?
Correct.
And I am applying the force in one particular direction. I am able to move the body linearly, correct?
Yes.
But if I have to apply, instead of 5 forces, I have to apply the force only at one point, let's say.
Yeah.
Are you able to understand?
Yeah. Yes, sir.
So if I try applying it at any other point, the body does not undergo linear motion. It undergoes what?
Rotational motion.
Right? Rotational motion. But if I'm able to figure out that one point, right?
That point, you're able to lift it.
Correct. And that point will be called as what?
Center of mass.
Center of mass. Where I will be able to lift it?
Easily.
Not easily. I'll be able to make a linear motion.
Right. Yeah.
If I make the same effort in any other point, what it will undergo?
Rotational motion.
Yes. So that point where if I concentrate all my forces at that point, I will be able to produce a linear motion.
Right, sir.
Is it clear now? Okay, good. Now, very simple. How do you find the center of mass? Suppose a body has masses in different places, X, Y, Z, or at least X, Y. Then center of mass, how do you find? x center of mass is given by summation of all the masses into the x distance divided by summation of all the masses. This will give you x center of mass. How do you get y center of mass? Same method. Add all the masses, multiply each mass with its y coordinate divided by sum of all the masses. This will give you the y coordinate of center of mass. Very, very important. All right. So let us do one question based on this.
Okay, sir.
Okay, I want you to go through this. Any one question. Okay, we can even go through a question from here or from my worksheet. Okay. Probably I'll choose a question from your worksheet, and then this you can examples you can go through. Okay.
Okay, sir.
So look at this question. So what is the question? 4 masses m, 2m, 2m are placed at 4 corners of a square. Okay. So I have a square. 4 corners, I have 4 masses. I have masses m, 2m, and 2m. Clear, Samuel?
Yes.
Yeah. So without any loss of generality, I can consider this as y-axis.
Right.
I can consider this as x-axis. Okay. So that your coordinates, finding the coordinates will become easier. Okay. What is the side of the
Yes.
square?
A.
A. So this distance is A. This distance is A. This distance is A. This distance is A. Right.
So we have to apply center of mass formula for 4 corners in this case.
Yes, yes, Sam. But then you will be able to do that only after you know the coordinates, correct?
Yeah.
So what are the coordinates? Let's start from this. What is the coordinate here, Samuel? I told you this is what? Origin, right? Because
Origin.
meeting point of y-axis, x-axis. So
0,
what?
comma m.
0, comma m.
M, comma 0. Sorry. M, comma. My God.
No, not m. 0, comma 0.
Origin, yeah.
Origin, correct?
Yeah.
Now, on the x-axis at a distance of a units, what will be the point?
M, comma a.
Not m, m is mass. Why are you mixing up mass and distance? What is the distance here?
A.
If you move on the x-axis by a units, what will be the coordinate?
A, comma 0.
Ah, very good. That's all. Okay, now tell me, what will be the location of this mass?
What's it?
What will be the location of this mass? 2m. This 2m.
2m, comma 0.
Huh? What? Samuel, why are you mixing up distance and mass? How is it 2m, comma 0? Where did 2m come? 2m is the mass. I'm asking you the position. I'm asking you the distance, coordinates, x and y, not mass.
A, comma 0.
A comma 0 is this point. Will this point also be a comma 0?
No.
Right? How do you say? Simple 2D geometry. How did you move from this point to this point? You vertically increased your height, correct or not?
Correct.
By how much
2a,
distance?
comma 0. 2a, comma 0. 2a, comma 0.
No, don't spurt out your, I've told you, right? How can it be 0? 0 is only on the x-axis, the y coordinate is 0, correct?
Yeah.
This point is not on the x-axis, right? It is in the plane, correct?
So,
First quadrant, correct?
right.
Think. Wait. What is x coordinate? What is the x coordinate here at this point, B? What is the x coordinate? Come on, tell me.
A.
A. So from this point B to C, when I moved, did I change my x? Did I move horizontally or did I move vertically?
Vertically.
Vertically, right? So horizontal value does not change. It will still remain A only, okay? But vertically, I have moved how much distance?
A.
A. So it will increase from 0 to
A.
So the point will be A comma A. Clear?
Yes.
Now tell me, what about this one?
A. Now you've increased it horizontally.
You're not increased, you come back,
From
right?
C to D. From C to D. Yeah.
Have you increased it?
No. Just maintain the horizontal distance. So.
No. You have moved horizontally. No doubt about it. But if you come back, it is a reduction in x value, right?
Yeah.
If you go from left to right, it is increase in x value. If you go from right to left, it is
Decrease in x value.
correct. So how much is the x value getting decreased by?
A minus A. So
Yes,
zero.
go ahead. So what is it?
0.
What about the y coordinate?
That remains unchanged.
Very good, very good. So do you understand the logic? Or you could have simply moved from O to D.
Right.
So this you must figure out within a few seconds, okay?
Right. Sir.
You will not have much time for this. This you must be adapt so that you are able to answer it in a second or two, correct?
Yes. Sir.
Yeah, okay, good. So now you have the x coordinates, you have the y coordinates. So I told you how do you find XCOM? So what is XCOM? You should add
Sigma mi xi by sigma mi.
sigma xi mi by sigma mi, correct? So that means in the numerator, you have to multiply each mass with its x coordinate. What is the mass here? Tell me, Samuel.
M.
What is the x coordinate?
0, 0.
No, x coordinate alone I'm asking.
A 0. At point 2, sir.
At point 2, what is the x coordinate?
0.
At point B, what is the x coordinate?
A.
At point C, what is the x coordinate?
A.
What is at point D? What is the x coordinate?
0.
Yeah, only those are important. Mass and the x coordinate. So what does it come on? Tell me. M into
0.
Plus
M into A.
yes.
Plus M into A.
Is it M?
Sorry, 2M into A.
Yeah.
Plus 2M into 0.
Yes.
Divided by M plus M.
M. That means you have to simply add the masses. What are they?
M plus M plus 2M plus 2M.
That's all.
So 0 plus MA plus 2MA plus 0 by 6M.
So this M into 0 will get cancelled, right?
Right.
So what do you get? 2MA plus MA. What is it?
2MA plus MA is 3MA.
Right. Divided by what?
6M. You get 1 by 2A.
Very good. A by 2. So XCOM is A by 2.
Now we need to find Y.
Now similarly, you should find YCY. Come on. Now you got the logic, right? First is you have to get the coordinates. Then once you got the coordinates, then it's just plugging it in the formula.
Right.
So come on, tell me now. Same way.
M into 0.
Yeah.
Plus M into 0.
Yes.
Plus 2M into A.
Yes.
Plus 2M into A.
That's all.
Divided by the addition of all the masses.
Which will give you what?
M plus 2M plus 2M, which is 6M.
Correct. That's all. So now you're clear about how to find center of mass, right?
Yes.
So what does this become? 2MA plus 2MA is?
2MA plus 2MA is 4MA. 4MA by 6M, which is 2A by 3.
Very good.
So we have A by 2 and 2A by 3 as the answer.
That's all. So you're getting the idea, right, Samuel?
Yes, sir.
Yes. You have another 5 minutes. Could we do one more numerical, or are you getting late for your class?
No, sir, you can continue.
One more numerical, okay. I'll go to the textbook. All this theory you go through. Yeah, we'll do this. This is very simple. Just mathematics. You go through this also. This also we have discussed how to do A dot B and A cross B.
Yes, sir.
Probably A cross B, I'll give you. I will take up a question and we'll do. So that
Okay.
you're thorough with this. Yeah, this is a typical question. Okay, right? So now, how do you do this? Let me help you understand. So find the torque. So what is the question? Question is about
Torque.
finding the torque. What is given? Force is given.
R is also given.
Yes. What is force?
7I cap plus 3J cap minus 5K cap.
Right. Then
Then
about the
R
origin,
also.
and the force acts on a particle whose position vector is, so position vector is given by R vector. What is position vector? What is R vector?
I cap minus J cap plus K cap.
Okay. I have given you the formula. Torque is obtained as what? Cross
R
product of.
cross R and F.
Okay. So how do you find R cross F is, how do you find cross product is using a method called determinants. You learn it as a complete chapter in 12th, okay?
Right.
But right now you will just know the evaluation method. You will learn the evaluation method. So the method is like this. First row must be filled with what? Look at the board and tell me. First row must be filled with?
The R vector. What was an R
No,
vector?
no, listen. First row. This is called first row, correct?
I cap, J cap, K cap.
I cap, J cap, K cap. Is it clear?
Yeah.
Second row must be filled with R caps coefficient, R vectors.
So 1,
Yes,
minus 1 and plus 1.
yes. The third row must be filled with what?
Force coefficients.
Yes. So what are they?
7, 3, minus 5.
Got it?
Yes.
Then how do you solve it, right? Do one thing. Just observe the board now.
Yeah.
So I cap. First, this is called evaluation along first row. So there is a convention here. Plus, minus, plus. All right?
Yes.
Plus I cap, minus J cap. Then what?
Plus K cap.
Yeah, this is a convention. Okay. Then what do? You make a smaller determinant of 4. I'm just telling you step by step so that you will not make mistakes. So what is that smaller determinant? Let me tell you. For I cap, that determinant, what you do is you cancel this column, you cancel this row. What are the elements you see, Sample?
Minus 1, plus 1, 3, minus 5.
Yeah, that's what you write. So you write minus 1, plus 1, 3, minus 5. Clear, Sample?
Yes.
Okay. Now, for minus J cap, for that, what do? You cancel that column, you cancel that row. What are the elements you see?
1, 1, 7, minus 5.
That's what you write. Come on, tell me. 1,
1, 7, minus 5.
Then the last one plus k cap. For that, you cancel that column where k is present.
1,
Also, you cancel. What is remaining?
1 minus 1, 7, 3.
Yes. This is called determinant evaluation. Okay. We're going to evaluate in the next step. We have made it into a simpler form now, and then we're going to evaluate now. Okay.
Yes.
Last step. So it is I cap into, how do you evaluate this is product of leading diagonal elements minus product of the other diagonal elements. So what do you do? Minus 1 into minus 5. What is it?
5 minus 3.
Exactly. Minus j cap into
Minus 5 minus 7.
exactly.
And plus k cap into 3 minus or minus 7.
Yes.
So you get 2 I cap plus 12j cap plus 10k cap.
Yeah, very good. So you get 2I cap. Come on.
Plus 12j cap plus 10k cap.
That's all. So this will be your torque. Torque unit is Newton meter. So you just have to answer and leave it there. 2I cap plus 12j cap plus 10k cap. So ideally, unit is also expected. Okay.
Yes.
Okay. So did you understand the process?
Yes.
Okay, good. So I think with that, we will stop today's session. Okay.